Good afternoon, everyone. Uh, Thanks for being here. My name is Yu Lin, and I'm going to talk about of CPU profiling and latency diagnostics in Java. So it's my first time being here, so I think it's better to do a little bit of introduction. These are the places I've worked for or studied in. And I started doing JVM about 5 years ago. And when I started, I do GC-related stuff, and so that it has become my go-to topic. And as you can see, I will use some of the examples with GC later in my talk. And I'm on here on behalf of Alibaba Cloud JVM team. And our team is primarily based in Hangzhou and Shanghai. Our team focus of recent includes cross-architectural performance, distributed data processing performance for Spark and Flink type of applications, and JDK upgrade and providing tooling, and many more. And these are the sort of the big ones, and also they are related to our talk today. And the Alibaba Java ecosystem is one of the most heavily Java-based ones. And it's currently primarily based on JDK 11. And it's slowly shifting to JDK 21 plus. And with a lot of legacy applications still running JDK 8. And in the past few years, we have created many unique techniques such as Wisp coroutine and multi-tenant and JGC. And you can look this up. And we are very keen on adopting the latest features from OpenJDK, such as Loom and Lilliput on 21. We're trying out the newer solutions to the pinning issues on 21, and we use JGC and Lilliput on 11, and we use G1 on 8. And a little bit introduction about our Java distribution. We maintain two Java distributions. One is called Dragonwell, and the other one is AJDK. And the first is open source. The second one is used internally. And these are both downstream distribution for of OpenJDK. And so basically, we will adopt the newest features and then use it internally. And from our special workloads or from our customers, we find that special needs, and then we create our own features. If we find that these are solving more common problems, then we might consider contributing it back to OpenJDK. And we are very proud that AJDK is now the ubiquitous Java distribution powering our e-commerce applications in Alibaba. And you can see everywhere in Alibaba. And to our knowledge, in terms of computational scale and production footprint, AJDK is probably one of the biggest, if not the biggest, deployment in China. And for Dragonwell, it can be found behind many of our cloud users, and it's also behind many of the big tech industry companies and in these industrial areas. Yeah, and that's it for the introduction. Let's get back to the main topic today. So this is the outline, and I'm going to talk about the background of the problem first, and then this includes what has prompted us to look into off-CPU factors in performance or latency issues, and what are the challenges we have identified, and I'll use a demo to work through our method, and then the method itself. So first of all, why off-CPU profiling? 3 reasons. First is that latency is the key performance metric. And actually it's probably the first metric that is perceived by users of an application because throughput issues can convert to latency spikes and prolong responses. And another part of that reason is the major contributors to latency are being off CPU. When we say off CPU, we mean that scheduling or I/O waits or networking. And this is more significant in very sensitive, latency sensitive services. And it has become more exposed as Java is becoming more postless. And the second reason is that in order to optimize workloads that exhibits both compute and I/O-bound characteristics at different times, we want to consider using a tool to help us to identify bottlenecks and help us guide our optimizations. This includes the Spark and Flink, like I mentioned earlier. And the third reason is that we want to enrich our cross-platform and full-stack diagnostic capabilities. I'll expand on this a little bit later. So first is that the trend in latency that we have observed. So around 2020 or before that, in our company, there's overwhelmingly using HJDK8 with CMS, GC, and it's very common to see latency spikes over 1 second. By the way, this one is from a very important application in e-commerce, and I'm using this throughout the whole example. And this application is representative enough, which means that we observe this over 1 second pauses very frequently. And I actually have a zoom in the graph that shows that there are occasionally 1 second spike caused by concurrent mark sweep. And then in the same test, in HJDK 11 with G1, we can achieve less than 300 millisecond max pause with mid to high tens of milliseconds for regular pauses. And meanwhile, some applications are starting to use ZGC, and the pause becomes even less significant. In more recent time, we have made transitions to HJDK 21, and this witnessed low tens of milliseconds. And typically, we can achieve 10% reduction from HJDK 11, as shown in the table on the right. And interestingly, we can, the young GC time reduce even more. We can reduce, for example, in this application, 25% to 30% young GC time. And notice that the proportion of GC pauses compared to the whole RT came down to just about 50%. In the past, it used to be 2/3 or more. So this means that at least for GC pauses, the significance of it is becoming smaller. And this is even more so for postless GC users. So if we want to optimize for RT, we will need to look elsewhere for bottlenecks. And a second point we're trying to make is the importance of I/O awareness. And we have here an interesting case of the importance of being aware of compute and I/O intensiveness. So I mentioned earlier that we care a lot about Spark performance, and our users that use Spark are typically very concerned about TPCDS benchmark, which is a benchmark that is used for evaluating the performance of data warehouse and big data systems. And there are 99 queries in this benchmark. and some of them exhibit heavy I/O bound. For example, Q28. I have this graph on the right that shows that during the execution of Q28, we have the blue line representing the user CPU and green line representing the I/O weights. So we notice that I/O weights is significantly higher than the user CPU, which means that it's heavily I/O bound. And then then we can look at the memory graph. It shows that in the instance, the memory is primarily occupied by heap, actually occupied by JVM, including the most significant part, probably the heap. And then the cache is just below half, is less than half of the used, which means that and it stays flat for the entire time, which means actually let's just remember it for now. And so the issue we are identifying is that JVM will try to push for throughput. There's heuristic in JVM that will try to push for throughput. For example, it will try to calculate the number of the GC process, and you try to keep it below certain ratio compared to the whole application time, and you push for throughput and expanding the heap. And in this case, if it's taking up all of the memory in the instance, then there's no space left for the cache to increase. And on the other hand, JVM is not actively trimming the ISS usage by default. So that's why even though we have really high I/O wait time, the cache doesn't increase. And by doing this, JVM hasn't been able to achieve throughput because that hasn't been the bottleneck, and the I/O bottleneck hasn't been addressed. So an optimization, an idea is that we can, instead of letting heap taking up all of the space, we can we can let it be aware of the current I/O wait time and shrink the ISS on demand. So on the bottom right graph shows that applying the optimization, we can shrink the JVM heap usage. And in return, when the program is trying to do file I/O, the I/O memory usage can finally increase. And this results in a reduction of the I/O weight, as seen in the green line in the top graph. And and in return, the user CPU can actually goes up because now it spends less time on I/O. And finally, there will be a balance. And then this optimization reduces a third of Q28 time from 52 seconds to 35 seconds and 5% total TBCDS time. So this really brilliant idea by one of my coworkers actually reminded us that perhaps sometimes we can let JVM be aware of the I/O and achieve improvement. And a third point we are trying to make is that as a cloud provider, we are sometimes caught between the transition between hardwares. For example, we often upgrade users' hardwares, and so there's transitions between architectures and vendors and generations of hardwares. And then users is going to compare the performance on these platforms, and they will ask for explanations, which requires sort of full stack diagnostics, which means that it's like a less controlled comparison between two sets of environments. The chance of a problem originating off CPU are as good as from on CPU. And the similar arguments can be applied to kernel space versus user space, and platform-dependent code versus platform-independent code. And it's very different situation from the more controlled comparison situation from just upgrading or swapping the software. And this is why we think that maybe we need a more quantitative approach to help us to first identify bottlenecks and then achieve a more clear explanation. And then 3 reasons, then we come to the challenge we identified. So first of all, we acknowledge that there are many powerful profilers already for Java. And what little difference can we make in addition to these profilers? Actually, profilers, there might be some limitations in latency profiling. First of all, perhaps the statistical representation is not very suitable for latency profiling. In latency profiling, we need more details than aggregated time as most profilers are using. And a second one is that occasionally we need to perform full tracing to reliably capture and analyze outliers rather than solely relying on sampling. And a third one is that we sometimes need to do a dependency breakdown. This can be better explained in the demo later. And on the other hand, we also have low-level system tracing and instrumentation tools, but they are not necessarily very Java friendly, meaning that they might not be capturing Java symbols, or you cannot specify Java entry points for instrumentation, and they might be hard to deploy in real complicated workloads, and there might be cross-platform availability issues. So next, I'm going to jump into our demo and hopefully explain our approach and what's the difference it can make. So our demo is taken from an issue I came across on SpecJBB. There's a strange latency degradation after a certain patch. And on the right, on the left, we have P50 readings from SpecJBB, around 900 microseconds. And on the right, we have the degradation, which is around 13 to 1500 microseconds. And I'll use this as a showcase to walk through our method. We will use our method, our tools to identify what's the root cause. However, this issue is probably comes from the SpecJBB's end, so it's not necessarily very important. The important part is that how do we use the tool to approach an issue like this. So given such an issue, what are our options? Of course, we can use perf-like tools to generate flame graphs. And flame graphs are usually very good for performance issues, but not necessarily this case, because a single transaction might not take CPU. It might be waiting on something. And so solely relying on CPU might lead to unclear results. And we can also use some profilers to capture thread lifetime, meaning that we can look at how much time it's blocked, how much time it's waiting and sleeping. But this approach lacks the dependency breakdown between threads, meaning that we might not know exactly what each thread is waiting for or block, what's the reason for the block. And it's probably hard to connect to a thread to a transaction, meaning that you don't know for a certain amount of time block waiting for something, how much is the time contribute to the latency of the transaction. And another method is probably instrument and log manually with the source code and do post-hoc analysis. This is probably closer to our to what we need, but it's the most expensive approach. Another option is, of course, using low-level system tracers. This will use the most rich information, but it's probably an overkill because it has a lot of overhead, and it has probably you give us the exact instructions that a transaction is executing, and that's probably not necessary. Instead, we are using a tool called RT Radar, and in this screenshot, I'm going to show you the way to invoke this tool and the step-by-step guide to use this tool to analyze the issue. So first of all, we need to specify the start and end of the transaction. We assume that there are basic understanding of the entry points of the transactions in question. So actually, I have a larger one. Yes. So this highlights how you specify methods to the tool, and it notes that from this method to the another method, you can consider it as a transaction, and you can enable your tracing. And then when we finish the tracing, we can do a report. We can invoke the report command, and the report will show us the complete transaction profile. This includes the average and P50 and P99 latency, and it can be listed in a per thread basis. And then, given this, we can actually look at the tool runs that we have seen earlier. On the top, we have the degradation run. We can capture its P50 latency, which is 1500 microseconds, same as the readings from SpecJBB. And then the normal runs is around 900 microseconds, same as the readings from earlier. So this shows that the tool stays faithful to the issues. And on the corner, we have a screenshot, recording of how we can screen out some of the outliers. We don't necessarily need this function, but it just shows that capability. Yeah, you can screen out, for example, outliers that takes longer than 2,500 microseconds, and yeah, you show you. And then this is the more interesting part of the tool. it will show you a breakdown of transactions. You can select any of the transaction, and it will show you what this transaction has been through. For example, we have here there is a zoom in, yes. It show you that the transaction depends on 4 threads. There are 2 injectors and 1 backend. And then it's sort of, you can understand that for each thread, how much time is spent on CPU and on scheduling and on waiting. And it's all shown on the top rows. And given this information, we can try to understand what makes a transaction longer. And this is, you can actually look at each one, and you'll quickly find that this is a very typical transaction. It looks like this. There are multiple injectors, and there's 1 backend. And it's always looking like this. And this particular transaction takes around 300 microseconds. And there are 3 injectors in this transaction, and this 1 backend. And for other transactions, you can select them, and there shows maybe 10 injectors or 20 injectors. So the only difference or the major difference between a shorter transaction and a longer transaction is the number of injectors in them. So you can basically plot this dependency graph in it, and there is 1 backend, and it starts from 1 of the injectors, and then it ends with 1 backend, and you also find out that there's 1 thread that is always originating. There's always starting the transactions. So all transactions always originating from the thread. So it has such patterns, but at this point we don't necessarily understand what that means. But we would like to call this, for now, we would like to call the first threads that initiates a transaction the scheduler, and then the rest of the injectors, we call them the submitter, and then the backend threads will be just the backend. And actually I have more, yes. So this captures the dependencies graph more accurately. There's 1 scheduler, and then there's multiple submitters, and then finally it goes to the submitter that actually submits the task to the backend. And then the backend finish processing the task, then they'll get back to the submitter. And this will finish the whole transaction. And the difference between a longer transaction and a shorter transaction is how many threads are in the middle. And actually, I have a longer one here, and you can see a shape like this. And this one is taking 1500 microseconds, and by the way, it's around the P50 of the degradation run, and it's consisting of many threads in the middle, and they are forming a sort of a wake-up chain. So basically, 1 thread, when they finish processing the task, finish executing whatever they are doing, then it wakes up another task, and then wake up another task. So this is, if you look at you play around with the tool more, you will know that if multiple threads are competing for lock or monitor, and then you exhibit a pattern like this. And also for a queue of tasks and multiple workers, then it's also exhibit a pattern like this. And yeah, this sort of shows that what is happening inside a super long transaction. And another thing we noticed that for longer transactions, there are more schedule in and schedule outs in the backend. For example, here we see that backend is on CPU for 30 microseconds, and then it goes out of CPU for 60 microseconds, and then in for another 6, and then out for another 100 or so microseconds. So this means that this backend is interrupted during its execution. Means that maybe there are other threads competing for CPU. And so with this understanding of a transaction, we can go to the next step to analyze them. So what we do is that we can filter the 10 transactions just below P50. So we can filter 10 transactions from the original run just below 900 microseconds. And then we can filter transactions from degradation run just below 1500 microseconds. And then we can look at how many threads that is in the way of a transaction. And on average, the original run takes 13 threads. And on average, on the degradation run, that takes almost double number of threads. And we can also look at how the sort of backend, how it behaves. And there's a pattern in the backend that shows in the corner here. We have the backend goes, it's doing something on CPU, and it suddenly goes back to the injector, and then it goes back to the backend. So this pattern is likely coming from a worker that finished processing a task, and then you wake up the thread that's waiting on the task. And then it continues to do whatever task that is left in the sort of pool. So this can be, we don't know exactly what it means. We don't know what exactly it do, but it can be the number of tasks it's processing. So the number of tasks can be calculated by the number of these patterns plus 1. And so given this data, and also this tool also shows you the average CPU and average scheduling time and average wait time during a transaction. And given all of this information, we can see that probably this degradation run is going through a busier queue, and this caused the scheduling cost to double and on CPU time to increase. And given that we set a fixed number of fixed IR, which means fixed number of transactions per second, this leads to the more probable explanation that there's a burst in transaction every once in a while, initiated by the task scheduler. And yeah, that's the demo. And that shows us that with this quantitative approach, we can sort of dig into a problem and then find the root cause of the problem. And yeah, so bringing it all together, the tool is extracting rich information for latency diagnostics by dissecting transactions into different parts, including scheduling between threads and waiting for other tasks to finish, and scheduling in and out of CPU. And with such quantitative information, we can further use this to guide our analysis and incentivize optimization. And this is non-intrusive. Failing to do so will disrupt the contentious nature of the issue, leading to unclear result. And it is thin and requires minimal setup, ready to plug in. And then finally, we will talk about our method, and it's not, it's actually very simple. It's just instrumentation plus picking up the relevant kernel events in the middle. So we have user-specified events, a starting point and an ending point, and we can pick up whatever happens in the kernel between these two events, and then analysis to find out that what's relevant in the event. For example, we have thread A initiating an event, an instruction, a transaction, and then it wakes up another thread. So you can actually see that by capturing the kernel events such as wake up, context switch, you can actually form a chain of threads that is in the middle of a transaction. And then this construct a unique dependency wheel of the transaction. And also this is why with queuing, with a task queue, we can see a wake up chain between workers because of this special mechanism. And a little bit of introduction about the instrumentation method. Instrumentation is done with a mix of logging and C callbacks. You can either do logging or C callback. C callback is for Linux uprobe mechanism to attach to. So you give it an address, then Linux uprobe can attach to the address. And if you execute that, an event will be logged. And I'll leave out details, but there are different costs associated with different logging mechanisms. And logs are usually carry more information because sometimes that many transactions happens simultaneously, and you need tagging to identify individual transactions and match the start event and the end event. So logs are usually carrying more information, which helps in this situation. And an intricacy lies in matching the start and end event of a transaction. For transactions that emit both events from the same thread, it's simple. You just match the start and end using the same TID. But for transactions that happens in a random place with different threads, it's actually very difficult to identify the connection between them. And for the interesting case of virtual threads, it's your platform threads sometimes change, and then you cannot use the TID to construct the transaction because the platform threads can be changed. So to address this, we use context identifiers that which basically means we match the context. The context consists of these and return values and method arguments and this type of information, and we can use the algorithms to match the events so that you know that even these events happen in different threads. If they have the same identifier, they can be associated and then forms a transaction. And speaking of virtual threads, we have this really cool feature in HJDK that automatically converts threads to virtual threads. And we can use this tool to help explaining its benefits. So we have, in this particular case, we can improve its P50 RT from 2300 microseconds to 1500 microseconds. And this improvement can be shown in the tool, can be explained by the tool. The tool shows that the Loom is using less than 5% of scheduling time, and the baseline is using almost 25% of scheduling time. And the reason Loom is able to achieve that is that the transactions actually completes within around 3 forejoin pool workers rather than many injectors or backends like I shown before. And you can also use this as a guidance in the development of virtual threads or the optimizations of virtual threads to see whether this situation improves or worsen. Yeah, it's a simple demo of, and then we can come to our summary. So as Java becomes more postless, we need to reevaluate how we approach latency issues and focus on Spark or Flink from our cloud users reminded us that JVM occasionally benefits from the awareness of I/O. And a position as cloud provider requires a stronger capability in quantitatively analyzing latency bottlenecks amid hardware competition. And hopefully we demonstrated the strengths of a profiling tool with the capability of breaking down latencies into contributing factors such as scheduling, I/O, and networking. And we highlighted how it is achievable and feasible with instrumentation and kernel event capture, and the unique will it can provide. We look forward to the opportunities for contribution based on our findings. Thank you.